Okay? So the way we're going to do that is get the Kaz to help us. So there's the mean. Okay? We want some multiples, 1, maybe 2 or close to 2, amounts of standard deviation. It's maybe not exactly 2, might be close to 2, and we just said 1.94 multiples of standard deviation on either side of the mean, so it shades in 0.95 area. Yeah? So we can say things like, oh, we're 95% confident that this is the interval that contains our desired value that we're after. And I'll elaborate more on what that means shortly. So we're going to use what's called the inverse normal probability function. And it's found on your Kaz. It's basically saying, okay, give us a probability and I'll give you a value of x, or a value along the line. Okay, that's the inverse function. The other functions, where it's not the inverse function, the normal function, is saying, okay, give me a value of x, tell me the mean standard deviation, and I'm going to give you the probability of observing that. Okay? That's the normal function. But we're going to do the opposite, the inverse, because we know what the probability is, 0.95. So what is the corresponding values for that? So can everyone find the inverse normal function on your Kaz? So you go to probability, then you go down to distributions. Okay, now the distribution we're looking at that we want to find probabilities of is the normal distribution. So you've got 1, 2, 3 up here. You've got your normal PDF, which is the probability density function. You've got your normal CDF, which you'll use, this one you'll use in methods and in SPECH next year, okay, to work out the probabilities of observing certain X numbers from a normal distribution, okay, and then there's the inverse normal function, and it gives you this little window. So this window here has a default value of 0 and 1. That's standard. Okay? It's called the standard normal distribution. Now, then the area. What does the area correspond to? Area of the graph, which is in terms of, it's 0.95. That's correct. It's our probability that we want to, what we're observing. Okay? So the area is referring to what is the probability, okay, that you're after. And I'll give you some X values in return. Okay? Alright, so we're going to use that. Everyone found that? Now, if you put in 0.95 there, what kind of number do you get?
It leaves the 0 and 1.
Yep. So 0.95, and you get?
1.64. Actually, 1.65 with my random method.
So who was closest?
Okay. Now, we said it needed to be closer to 2. Yeah? Because exactly 2 standard deviations from the mean was 96%. Yeah? We want to observe 95%. So we said it had to be pretty damn close to the number 2. We got 1.64. That's not that close, is it? Alright. It's because, unfortunately, it's not that simple as plugging in 0.95. Okay. Now, why isn't that simple? Well, life is not that simple. Well, the way this function works, this is the programming of your Kaz. It's not crazy math. This is just the way your Kaz has been programmed. Okay? The Kaz has been programmed to solve this equation. This is a probability equation, or an inverse probability equation. It's saying the probability that x is less than or equal to some number. That's the direction of the inequality for this equation. Okay? Alright? Now that is equal to then the area amount that we put in here. maybe not 0.95, that's the area that we need to observe. That's the area in the function. Okay, now we have to get we got to select the correct area such that it corresponds to the direction of our inequalities. So you've got to relate it to the numbers on the number line. So there's your number line. Going this way is positive numbers, going that way is towards the negative numbers, or going down towards 0. Okay, so just indicate which way do you think the numbers we're observing at, we're trying to observe when we're looking for x numbers that are less than a certain value. Which way are we going? We're going to the left, aren't we? We're going this way to get numbers less than a certain value. So we need a certain value, say maybe there, okay? And then we want all the x numbers less than that value. So it's all these numbers going to the left, okay? Now on the graph, that's going to correspond to this amount of area. Okay? So that's the amount of area the CAS wants. The tail area. So when we have a full 95% in the middle from there to there, we got to work out what does that correspond to, okay, in area in the tail. How do we work that out? How do we think about that? 1 minus 0.95. Okay, so 1 minus 0.95, which is 0.05. Now, what is that? 0.05. Area of? Jovic? Whatever's remaining, isn't it? If the whole lot is 100%, then this is the leftover of the 95%, isn't it? Which is the leftover area of the shaded region. What is the leftover area? It's both. There and there. So then we have to halve it, don't we? Yes. 0.025. There we go. Does that make sense, how we work that out? So that is the leftover area. That's the area of this little shaded region that corresponds to x numbers on this scale here. All these x numbers. Okay? That is less than some value. That's what this is saying. That's what's been programmed into this inverse normal function on your CAS. Okay? So try it again. What do we get if we put the 0.025 in the area?
Negative.
Yep. Negative what?
1.96.
1.96. Negative 1.96. Okay. 1.94. He's pretty close. Okay, the fact that it's negative is not a concern. Okay? Now, why isn't it a concern? Well, if this here is 0.025 and over here is maybe towards the negatives, okay, then what's the amount of area in this tail? The same, 0.025, okay? But it's on the other side. Yes, the direction. So you've got the negative direction, you've got the positive direction. Now, what you did, you had a mean of 0 and a standard deviation of 1. This is called the standard normal curve, the standard normal distribution, okay? So it's basically a template, a standard person, well, standard distribution of curve. So imagine there was, you know, the standard human. Boom. There he is, standard human. Alright? Whatever he looks like, or she, whatever they look like, we don't know. Maybe agendered. May not be male or female, just standard, boom. Okay? And then you get all the possible variations, which is, the world, from the standard human. Okay? So there is a standard normal distribution. And then from that you get all the different possible distributions of sizes, of positions, of widths, yeah? Like we observed under the CAS before. So the standard normal distribution is a mean of 0, standard deviation of 1. Okay? So it's situated, still looks like that. But the mean is 0. Then you've got your positive x numbers. Then you've got your negative x numbers. Standard deviation of 1. So you've got then a negative 1, 1 standard deviation, negative 2, 2 standard deviations, negative 3, 3 standard deviations, and so on. Positive 1, 1 standard deviation. Positive 2, positive 3. Okay? 3 standard deviations. Does that make sense? So what we observed was the tail here. Okay? But there's the equivalent tail over here. Yeah? And that area was 0.025. That area is 0.025. Okay? Now, we calculated for that area of 0.025, okay, we get, if we look at our interval, and for our standard normal curve of mean of 0, standard deviation of 1, yeah, if we put that in our interval of there, 0, standard deviation of 1, yeah, then the interval becomes from a minus z to a positive z. Same number z, just one is negative, one is positive. Does that make sense? So here is the negative z number, while here is the positive z number. Same z number, just one is to the left, one is to the right. Corresponding to the exact same area of 0.025, 0.025. Does that make sense? Okay? So the CAS worked out this for us. Z is less than, because we looked at this particular area, because it's programmed in the CAS, it has to be some less than number. Okay? That's why it gave us the negative version. But it's the exact same value. Okay? So Z can be both plus or minus 1.96. And because we've got both positive and the negative of the same number, that's what we're showing here in the interval. We've got the negative version where you subtract the Z multiple of standard deviation, and then you've got the positive version where you add the Z multiple of the standard deviation. Both the positive and the negative of that Z number going that way, going that way.
So the Z being 1 or plus 1 or minus 196, it's only for negatives.
Yes, exactly correct. That's only for the 95%. Okay, so what we have now, the interval, okay, of the mean minus 1.96 standard deviations and the mean plus 1.96 standard deviations, the probability of observing that is 0.95.
Oh, why didn't I say that before? You already had that number when you said what it was earlier.
Yep. Okay. So when we say we're 95% confident, okay, then we form the interval using this little expression. We start with the mean, we subtract 1.96 of the standard deviation, okay, to get the minimum number. To get the maximum number, we start with the mean, and then we add 1.96 of the standard deviation. Yes, absolutely. You do any percentage of confidence. You can do 90% confidence, you can do 80% confidence, you can do 99% confidence. Okay? So, big pharmaceutical companies that sell cancer drugs, okay, they need to be very confident that their drug, okay, yields a result.
Yeah.
So they're not going to allow for 5% error. They're not going to say, oh, I'm 95% confident that this drug won't kill you. They need to, for their product to be viable and acceptable on the market, they need to be 99% confident that the drug won't harm you. Okay?
Like a 1%.
So being 99% confident, what it's going to do is increase
Thank you, Josh.
the probability, and it's going to increase the amount of shaded region beneath the graph, which gives you a wider, from there to there, it's going to give you a wider interval,
Do you have anything more
a
than
bigger interval. So we're saying, you know, we're 99% confident that if you take this drug, you will get well anywhere between 1 day to 4 years. Okay, it's because the width of the interval has to be much bigger. Okay. Yes.
Do you have anything more than 100% confident?
No. Because there's no more probabilities greater than 1. Yeah.
I'm great.
All right. Now, in what situation do we want to form a 95% confidence interval? So,
Like when your parents try and promise you something.
when their parents trying to promise you something,
That's just.
the parents might say, well, we're 95% confident we'll buy you your car,
Yeah.
okay, as long as you get anywhere between a study score of
99.
30 to 40.
Yeah. All right.
49
Now-
to 50.
If we don't know something about a population, if we are investigators, if we say we want to know, you know, the example is something about our school. So we survey. We don't know, we can't survey the whole school. We're just going to survey a sample. Okay? But we want to use the results we get from our sample to infer something about the whole school, about the whole population. So, if we don't know what are the population parameters, we don't know what maybe the population proportion is, we don't know what the mean is, the sample, the population mean is, we don't know what the population standard deviation is. Okay? If you don't know the facts about the population, then we use the sample statistics as your best estimate. Okay? I'm going to survey 20 people, and I'm going to take the sample mean of my survey, and I'm going to use that to say things about the population. And I'm going to speak about the population with a degree of confidence. Because I can't be perfectly certain that this sample that I took represents the population, because samples vary. Samples have a distribution. They're random. Yeah? But we can speak about the population with a degree of certainty, degree of confidence. Alright. So we get our sample proportion, our sample mean, or our sample standard deviation. Okay? So these vary depending on every time we take another sample, we're going to get different values. Okay? And we saw that in our simulation. The distribution of these values. Yeah? We see how they vary. So because they vary, because they're subject to randomness, then any confidence interval we form is an approximation. It's an approximate confidence interval. We can't be 100% certain. Okay? Now, we're going to look at some examples to construct this. Alright? First off, we're going to think about finding the 95% confidence interval for population parameters. So, such as P, proportions. So let's look at the situation where we're forming confidence intervals using a proportion P. So, the first thing we're going to look at is the first question. Everyone got this handout? We're going to look at question 1, please. Okay. 30 people were surveyed. 78% said that they like breakfast in bed. How nice. So let's estimate the proportion of the population that like breakfast in bed. Okay? So you can make judgments about the whole population just based on a survey of 30 people. And that's what they do all the time when they report things in the newspaper. Okay?
I have 3,030 people.
Yeah, same here.
We should.
Yeah, you guys just crossed out one of 30.
Sorry, yeah. Maybe I doubled up when I cut and paste.
I like this sample.
Can we just use 30, please? So cross out one of the 30s. Okay. So we've got 30 people surveyed. 78% said that they like breakfast in bed. Estimate the proportion of the population that like breakfast in bed. And we're going to find a 95% confidence interval for that estimate. Alright? So, when we find the general structure for a confidence interval is the mean minus 1.96 standard deviations to get the minimum, and then mean plus 1.96 standard deviations to get the maximum. Now, when we're talking about the proportion, population proportion P, okay, we don't know anything about what is P in the population. Okay, it is unknown. What is known, perhaps, is the 78% said they like breakfast in bed from a survey. That's your sample. So if that is the proportion of the sample, what do we call that quantity? It's not P.
P hat.
P hat. That is your P hat. Very good. P hat. Okay, your sample proportion. Okay? So we use the sample proportion as the best estimate for the population. Now, the mean, we have to think about this is the mean of standard deviation of the normal distribution. Okay? And the proportion, sample proportion is normally distributed, approximately normal distributed, has that bell-shaped curve when the sample is large, or large enough. Okay? So we're after the mean of the sample proportion. And we're after the standard deviation of the sample proportion. Okay? So what's those values? What's the mean or the expected value of the sample proportion, of the distribution of sample proportion? What's that the same as? P. Very good. Do we know P? No. So what's the best estimate for P? P hat. Okay? So we'd have to use the P hat value as the best estimate because we do not know what the population proportion is. Okay? Alright. Now, what is the standard deviation of the sample proportion? That's that formula. Root P 1 minus P on N. Now, do we know what P is? No. So what's the best estimate for P? P hat. Very good. So it becomes P hat of 1 minus P hat over N. So we have to use the sample proportion value. And because it's just an estimate now. It's not the true number. Okay? Does that make sense? Alright. So we've got to use those rules and construct, using this structure to form our estimate. So first off, let's get the minimum value. So the minimum value is the mean of p hat, the expected value of p hat distribution minus 1.96 of the standard deviation of p hat. Now, that is, the mean is p hat number. And then we subtract 1.96 times the standard deviation of the distribution of p hat, which is this formula. Now, okay? So let's plug in our values. What's the value of p hat from the question? 78%, so 0.78. Okay, minus 1.96 times the square root of. Now we've got this 0.78 times. Now 1 minus 0.78. Good. Divided by n. And n is our sample size, which is 30. And there's your calculation. And that gives you the minimum value. Alright? So you set that up on your CAS and you set it up and evaluate. Okay. Alright. Then we do the maximum value. Now the maximum value is the same thing, but it's just the mean plus 1.96 standard deviations, okay, which using this structure, but now instead of subtracting we're adding 0. Point.
You got a negative.
Yeah, you probably
Check
did.
it again.
I got 0.63.
Try it again. Okay. So what kind of values did we get?
63.
So 0.63 to 2 decimal places. Now, when you do it on the CAS, you just press up on the arrow, select the previous line of working out, hit enter to bring it down, and you just change the negative into a plus. Okay, so you don't have to retype it all.
0.93.
Okay. All right. Now, we've got our minimum value, we've got our maximum value.
Maximum minus 1%.
Okay, no. So now we form our interval like this. All right. And there's two ways you can do it. The last thing is that we are stating our results, we're stating our confidence interval, and we're speaking about it with 95% confidence. So we can say, therefore, we are 95% confident that between 63% and 93% of the population.
Is it population proportion?
Yes, these are our estimates for the population proportion P. That's correct. We've just got a width of possible values where the true population proportion P will lie. Okay? Between 63% and 93% of the population, yes, they like breakfast in bed. Okay? So we're 95% confident that that's the case. Now if we wanted to say we're 99% confident, then the width between, the minimum to the maximum will be greater. It might be 50 to 99% for the population proportion. And if you've got a greater width in your interval, you can be more confident that the true value lies in that spot. Does that make sense? Yep. The only way you can know for certain what is the true proportion of the population that like breakfast in bed is you have to ask every single one. You've got to conduct the census. Yes? That's what the Australian government does, and we know how well that works out. Yeah?
They get a lot of money out of that because no one does it.
Yeah. Alright. Does everybody understand the structure, how we did that? So that's how we form, and you always answer, you get your two values by doing these two little formula calculations, and you write a little conclusion like that. Alright? This is how you report your results. Alright. Now, let's do one more. We're going to find 95% confidence interval for the population mean. Okay? So I want you to think about the mean value and the standard deviation value for the distribution of all the sample means. What are those formulas? Look them up. Alright, so now we're going to look at the situation where we've got a measured quantity, we're finding the sample mean. Alright, so 75 Victorians who were surveyed, the average amount spent on holidays this year was 2,314. Okay, so that becomes your sample mean of the survey. And with a standard deviation of 567. That's the sample standard deviation of the survey. So let's find a 95% confidence interval for the average amount spent on holidays by Victorians. Okay, so in this situation, to find the confidence interval, it's the mean minus 1.96 times standard deviation, mean plus 1.96 times the standard deviation. Okay. Now, we're thinking about a measured quantity, the mean value. So, we're after the mean of the sample mean distribution and the standard deviation of the sample mean distribution. Okay? So, what is the mean value or the expected value of the sample mean distribution? What's that the same as? The mean, the population mean. So the actual mu value of the population. Do we know what that value is? No. We don't know what from the information, there's nothing about, the whole population of Victoria and how much and the average value they spend on the holidays. What do we know though? The sample mean. There it is. So for 75 Victorians, that's your N, your sample size. Okay? The average spent on the holiday is this amount. That is your sample mean. Okay? So if we don't know the actual population mean, then the best estimate for that is the sample mean. That's the only information we get. So we have to use the sample mean as a way of estimating the actual true population mean. And we're going to use that as your estimate for the expected value of the distribution. Alright, for our confidence interval. Okay, now, what about the standard deviation of the distribution of sample means? This is the formula, which is sigma on the square root of n. Very good. That's the one. Okay? Now, do we know the actual standard deviation of the population? No. So what do we have to use as the best estimate? The sample standard deviation. Excellent. So this is what this guy is, the standard deviation of the sample. That is your S, is the sample statistic. So when it's not there, we don't know it, we have to use the sample standard deviation. Okay? And that is 567 divided by the square root of 75. And there it is. Okay? So then we use those quantities now to form our confidence interval. Does that make sense? So we've got to work out the minimum value of this confidence interval. The minimum value is the first one, where we subtract 1.96. So we get the mean, which is 2314, subtract 1.96 times the standard deviation of the distribution.
65.
Yep.
Do you want us to leave it like that? Or?
No, work it out all together. So that's your calculation that you got to do in your CAS, and you calculate the value.
I know. I was talking about. You know how we got the.
Well, with that, we got to do that calculation anyway. So you can write it like that. Write it like that. That's fine.
Leave it for the last minute.
Leave it. Write it as an exact value, but then do it the whole lot together as a calculation. Okay. So then, what's the max value? You take the mean of the distribution, and now you add 1.96 times 567 on the square root of 75. Okay? And that becomes your whole calculation that you do on the CAS. Okay? So what kind of values do we get? Set it up on your CAS. 2,185.68 or $7. Okay, as the minimum value. What kind of maximum value do we get? 2,442.32 or 0.3, 30 cents. Yep. 70 cents and 30 cents. There we go. Alright, so that's your interval that we formed. So therefore, find 95% confidence interval for the average amount spent on holidays. We are 95% confident that the average amount spent on holidays by us people, Victorians, is between, yep, the minimum to maximum, 2,185 and 70 cents and 2,442 and 30 cents. And there we have it. Okay? So the true average spent by Victorians is in between those two numbers. Okay? And we're 95% confident that is the case. The only way we can work out how much they've actually spent is by asking every single Victorian. Okay? Which is a census. Okay? Which is not very practical. Especially when it's done online. Yeah? Alright.